Look up just after sunset. There is a star that doesn't twinkle. It's the brightest thing in the sky, steady, confident, and named for the goddess of beauty. That is Venus. For centuries, we imagined a twin Earth. Early sci-fi writers saw a jungle world, warm, wet, and teeming with life beneath thick clouds. They were spectacularly, terrifyingly wrong. When we finally sent probes, we didn't find a jungle. We found a nightmare. Venus is the most extreme environment in the solar system. A surface hot enough to melt lead, an atmosphere that crushes like the deep ocean, and clouds made of pure sulfuric acid. But here is what keeps scientists up at night. It didn't have to be this way. Evidence suggests that billions of years ago, Venus had liquid oceans. It was a world like ours. Then something went wrong, something irreversible. Tonight, we're taking a tour of our twisted twin. We'll travel from the scorched surface to the temperate clouds, following the path of the heroic Soviet engineers who first touched its soil and the new missions heading back today. As we go, remember this. Venus isn't just a cautionary tale. It is a message written in 460 degrees of heat and a crushing wall of CO2. The only question is, are we listening? Chapter 1, The Deceptive Twin. Let's start with a comparison. Earth, 12,700 kilometers wide. A rocky world with a breathable atmosphere and liquid oceans. Venus, 12,100 kilometers wide. 80% of Earth's mass. A rocky world, just one step closer to the sun. On paper, these aren't just neighbours, they're a matched set. If you were building a solar system, you'd assume they shared the same history, the same future, and, given the right conditions, the same life. For a long time, that's exactly what we believed. Before we could pierce those thick clouds, Venus was the great blank canvas of the solar system. Serious scientists speculated it was a tropical paradise, a warm, wet world of swamps and dense vegetation. Science fiction went further, imagining a world of dinosaurs and adventure just waiting to be explored. It's easy to laugh at that now, but it wasn't an unreasonable guess. The logic was sound. The universe, unfortunately, doesn't care about our logic. What we couldn't see from Earth, what we didn't know until we arrived, is that those clouds aren't a canopy over a paradise. They are a lid, a thick, suffocating lid that has been trapping heat for hundreds of millions of years. Beneath that lid is no jungle. It is nothing a human mind could have pictured before the space age. And the most unsettling part, it didn't start that way. The hellish, crushing, melting Venus we see today is not the planet that formed 4.5 billion years ago. Something happened. Something took a world that likely had oceans and a climate like ours and turned it into an oven. As we move forward, I want you to hold one image in your mind. Two planets, born from the same cloud of dust, in the same neighborhood, at the same time. One became a home for rainforests and oceans. The other became a graveyard. Same starting point, completely different endings. That should unsettle you. It means the Earth we know isn't the default setting for a planet. It isn't inevitable. It was lucky. And luck, as Venus shows us, has a habit of running out. Chapter 2, The Lost Oceans. I want you to imagine Venus as it once was. Not the hellscape of today, but the Venus of 3 billion years ago. Picture an ocean, a real global ocean, pulled by the tides of a distant sun. The air is thick, but the temperatures are warm, even comfortable. This isn't science fiction, it is the current scientific consensus. Models suggest Venus held liquid water for up to 2 billion years. To put that in perspective, complex life on Earth is only about 600 million years old. Venus may have hosted the stage for life for more than 3 times that long. We don't know if anything lived in those oceans, but the conditions, they were perfect. So what went wrong? The short answer: the sun grew brighter. Stars evolve, and our sun has been pumping out more energy for billions of years. Earth, sitting further out, has natural feedback systems to handle it. Venus, closer to the fire, had no such margin for error. As the planet warmed, the water began to evaporate. Here, physics turned cruel. Water vapor is a greenhouse gas. More evaporation meant more warming. More warming meant more evaporation. It was a runaway feedback loop with no brakes. The oceans didn't just drain, they boiled away. As water vapor rose into the upper atmosphere, solar radiation shattered the molecules, stripping the hydrogen into space and binding the oxygen into the rocks. Then came the second blow. The shield failed. Earth has a global magnetic field generated by our churning iron core. It acts as a permanent shield against the solar wind, that constant stream of charged particles firing from the sun. Venus has no such shield. Without it, the solar wind didn't just strip the water, it scoured the atmosphere raw. What remained was a planet with no water, no protection, and an atmosphere of pure carbon dioxide. And carbon dioxide, as we know, traps heat. It traps it with terrifying efficiency. The temperatures climbed and climbed and kept climbing. I'm telling you this now because I don't want you to think of Venus as a planet that was always broken. It wasn't born hostile. It was a living world until it tipped. Scientists call Venus uninhabitable, but that word is too sterile. Venus didn't start that way. It became uninhabitable. It was a cascade of changes that fed on themselves until there was no return. And the mechanisms that killed Venus, they aren't alien. They are the same systems operating on Earth right now, being nudged in the same direction. Venus never got a warning, it just changed, and then it was too late. We have something Venus didn't, the ability to look at the wreckage next door, understand it, and make a choice. Whether we make the right one is a question for later. For now, let's descend into what Venus became. Because if this chapter is the tragedy, chapter 3 is the horror. Chapter 3, the great pressure cooker. Let's talk about what Venus actually is. So I want to give you some numbers, but I don't want you to just nod and move on. These deserve a moment of reckoning. The surface temperature, 465 degrees Celsius. To put that in perspective, lead melts at 327. Zinc melts at 419. If you placed a lump of tin on the surface, it would puddle in seconds. If you transported a standard household oven to Venus, that oven would be the coldest thing for miles, and it never cools down. Because Venus rotates so slowly, night lasts for months. The atmosphere is so thick and efficient that the heat is distributed perfectly. The poles are just as scorching as the equator. There is no weather on Venus, only a permanent, relentless state of baking. Then there is the pressure. Standing on the surface, you would feel an atmospheric weight 92 times greater than what you feel on Earth. To find that equivalent pressure here, you would need to descend nearly a kilometre beneath the ocean. Our probes had to be engineered like deep-sea submersibles just to survive for a few minutes. The atmosphere doesn't just make the planet hot, it crushes it like a fist closing. And the clouds? From a distance they look beautiful, bright, white and reflective. But those aren't water clouds, they are droplets of concentrated sulfuric acid. Technically it does rain acid, but the droplets never hit the ground. They evaporate 30 kilometres up, rise again, reform and fall. It is an eternal cycle of acid storms that go nowhere and achieve nothing. So, how did it get this bad? It comes down to carbon dioxide. On Earth, CO2 makes up 0.04% of our atmosphere, a tiny fraction that keeps us habitable. On Venus, it is 96%. This created a greenhouse effect so extreme that the planet cannot shed heat. Energy pours in from the sun, bounces around that thick atmospheric blanket, and has nowhere to go. Venus has reached a terrible equilibrium. It found its new normal. This is what a runaway greenhouse effect looks like when it is finished. Venus is locked. It is locked by physics, by chemistry, and by the irreversible loss of the systems that once regulated it. I want to be clear, we are not Venus. We have margins of safety that Venus did not. Our distance from the sun, our geological cycles, our magnetic shield, our outcome is not inevitable. But the mechanism, the gas, the physics, they are the same. Venus isn't just a warning from a neighbour. It's a warning from a potential future. It didn't happen overnight. It crept up over millions of years through incremental changes that fed on each other until the planet tipped. We are currently watching those same mechanisms operate on our own home. The question is whether we understand the wreckage next door before our own luck runs out. But enough of the atmosphere. Let's head down to the surface, because the ground beneath that crushing weight has its own remarkable and equally terrifying story to tell. Chapter 4. A world turning backward. Let's take a breath. We've spent our time in some dark territory, lost oceans, crushing pressure, and acid rain. Before we descend to the surface, I want to talk about something that isn't just horror. It's just plain, profoundly weird. Venus is the rebel of the solar system. Every planet follows a set of unspoken rules. They spin on their axes as they orbit the sun, a legacy of the cloud of gas and dust from which they were born. Almost all of them, Earth, Mars, Jupiter, spin the same way. Counterclockwise. It is the default. It is what you expect. Venus spins the wrong way. If you somehow stood on its surface, you would watch the sun rise in the west and set in the east. But that is only the beginning of the anomaly. Venus doesn't just rotate in the wrong direction. It rotates with an almost contemptuous slowness. The numbers here are staggering. 1 Venusian day, 243 Earth days. 1 Venusian year, 225 Earth days. On Venus, a single day is longer than its entire year. The planet completes a full trip around the sun before it has managed to finish one rotation on its axis. If you were born on Venus, you wouldn't even have seen your first sunrise by the time you celebrated your first birthday. This isn't a rounding error. It's a fundamental defiance of the norm. It drives the planet's weather in bizarre ways. While the surface sits in a state of nearly total stillness, the cloud tops, driven by hurricane-force winds of 350 kilometers per hour, race around the entire planet in just 4 Earth days. So, how does a planet end up like this? There are 2 leading theories, and both are incredible. The first is a catastrophic collision. Early in our solar system's chaotic youth, Venus may have been sideswiped by a planet-sized object, knocking it off its axis and forcing it into a reverse spin. The second theory is more unsettling. It suggests that Venus's thick atmosphere, pulled by the gravity of the sun, acted like a brake. Over billions of years, the friction between the atmosphere and the surface gradually ground the planet's rotation to a halt and eventually nudged it into reverse. Regardless of the cause, the result is the same: a planet permanently altered. This connects back to our big 3 tragedies. Our Earth's magnetic field, our shield, relies on a core that churns and a planet that spins at a healthy clip. By slowing down to a crawl, Venus may have effectively strangled its own internal dynamo. Without that spin, the shield vanished. Without the shield, the atmosphere was stripped. Everything on Venus is connected. Pull on one thread, the rotation, the collision, the heat, and the whole story unravels. Philosophically, this is a heavy realization. We have a deep human instinct to see our own normal as the standard for the universe. We assume days are shorter than years and that planets spin counterclockwise. We think these are rules. Venus is a reminder that the universe makes no such promises. Our predictable, life-sustaining world is not the template. It is one outcome among many, a lucky result of a particular history, a specific set of collisions, and a unique gravitational dance. We got the default setting for life. Venus got something else entirely. All right, we've spent long enough in the clouds and the abstract. It is time to go to the surface, because the ground beneath that crushing weight has its own story to tell. Chapter 5: The volcanically scarred surface. There is a practical problem with studying the surface of Venus. You cannot see it. Those thick, unbroken acid clouds are completely opaque. Point a camera at the planet, and you get nothing but blinding white haze. For a long time, the surface was a mystery. Then we started using radar, bouncing signals through the clouds to map the ground beneath. What we found was a world unlike any other in the solar system. Venus is a graveyard of fire. It is home to more volcanoes than any other planet, over 1,600 major ones and hundreds of thousands of smaller ones. 80% of the surface is covered in flat, hardened lava plains. But it's not just the scale, it's the shape. We found pancake domes, circular, flat-topped structures, 60 kilometers across. They looked like someone dropped a blob of thick dough onto the landscape. They were formed by viscous, stiff lava that oozed upward and hardened in place. Then there are the coronae. These massive ringed structures look like bullseyes thousands of kilometers across, formed when plumes of heat welled up from the deep interior and collapsed the surface beneath. But the biggest question remains: is the planet still alive? For decades, we thought Venus was geologically dead. We were wrong. Recent data has revealed thermal anomalies, spots that are significantly hotter than their surroundings, that seem to change in shape and temperature over mere decades. In one archival scan from the 1990s, scientists found evidence of a volcanic vent that changed shape in just 8 months. Venus may be volcanically active right now. This adds a layer of mystery to another strange fact. Venus has almost no impact craters. On the Moon or Mars, craters are everywhere, a record of billions of years of cosmic collisions. On Venus, there are fewer than 1,000. The thick atmosphere burns up smaller meteors, yes, but that doesn't explain the lack of large ones. The leading theory? Global, catastrophic resurfacing. Around 500 million years ago, a blink of an eye in geological time, Venus may have essentially repaved itself in a planet-wide volcanic flood, burying every crater in existence beneath fresh lava. It is a planet that periodically erases its own history to start over. Picture the surface today, a dim, orange landscape, where the thick atmosphere filters sunlight into a permanent, eerie amber twilight. The ground is dark, volcanic rock stretching to the horizon. It is perfectly silent, perfectly still, and utterly hostile. Nobody has ever stood there. No human eye has ever seen this world directly. But we have photographs. Grainy, amber-tinted, hard-won images sent back by machines we built. Machines that survived only long enough in that furnace to transmit a few final, precious frames before the planet destroyed them. That is the story we tell next. Chapter 6: The Graveyard of Probes. In the 1960s, at the height of the space race, while the world looked to the moon, a group of Soviet engineers quietly accepted an impossible challenge. They wanted to land on Venus. They weren't just building a spacecraft, they were building a suicide mission. They were aiming for a surface hot enough to melt lead, with an atmospheric pressure 92 times that of Earth. The program was called Venera. For 2 decades, they threw everything they had at the planet. Early probes were crushed during descent. Others were fried before they could transmit a single byte of data. Each failure was a data point. Each destroyed probe was a lesson. They kept going back to the drawing board. They eventually built probes like deep-sea bathyspheres, titanium pressure vessels cooled before entry, designed to survive for a thermal budget of just 60 minutes. 60 minutes! That was the dream. In 1970, Venera 7 became the first human object to land on another planet and transmit data back to Earth. It survived for 23 minutes. In 1982, Venera 13 landed, survived for 127 minutes, and sent back the most detailed images we have ever seen of the Venusian surface. Look at those images. You will see sharp, angular rocks and flat, dark flagstones bathed in a permanent, eerie orange twilight. You can see the edge of the lander itself in the frame, a testament to the machine sitting there enduring the furnace, transmitting data as it was slowly being destroyed. The images are not beautiful in the way we usually think of space photography. They are stark, grainy, and claustrophobic. But they represent the physical embodiment of human curiosity. These machines had no awareness, yet they performed beyond any logical expectation. When the heat finally soaked through the insulation, the electronics failed and the transmissions stopped. The probes became part of the landscape they were sent to document. Silent, crushed, melted lumps of metal sitting on the surface of Venus to this day. We haven't been back since. The last Venera lander touched down in 1982. For over 40 years, we have mapped Venus from orbit with radar, but no human-built machine has stood on that surface. We have sent rover after rover to the manageable surface of Mars, leaving the most hostile world in the solar system largely untouched. But the Venera engineers taught us something essential. An hour is enough. 60 minutes of data, 60 minutes of photographs, 60 minutes of contact with the most alien surface in our solar system is worth the cost, the effort, and the risk of losing the machine entirely. The graveyard of probes is finally going to have company. New missions are being built right now. But before we look to the future, we need to look up. Because there is one more environment on Venus, one more place where the temperature and pressure are, by Venusian standards, almost welcoming. We're going up, a long way up. Chapter 7. The Search for High-Altitude Life. We need to go up. Leave the surface, the crushed, melted probes, the silent volcanic plains, and the orange twilight. We are climbing 50 kilometers into the sky to a layer of the atmosphere that nobody talks about nearly enough. At 50 kilometers, the atmosphere is thin enough that the pressure is almost identical to what you are feeling right now in this room. The temperature is a mild 0 to 70 degrees Celsius. It is, by Venusian standards, a temperate zone. It is almost Earth-like. Not green, not lush, but physically stable. For decades, scientists have speculated that microbial life might ride the updrafts here, metabolizing chemicals in the acidic haze. Then, in 2020, the world erupted. Astronomers announced they had detected phosphine, a gas that, on Earth, is almost exclusively produced by industrial plants or anaerobic bacteria living in swamps and marshes. The implication was electrifying. Was something alive in the clouds of Venus? What followed was one of the most intense periods of scientific scrutiny in recent history. Other teams dove into the data, ran the numbers, and questioned the models. Over the following months, the picture became complicated. The original signal appeared weaker than reported, and alternative explanations involving sulfur dioxide chemistry began to emerge. The current scientific consensus. The phosphine detection is likely not a sign of life, but here is the most important part. The walk back of that claim does not close the door. The temperate zone still exists. The chemistry of the clouds is still a mystery. We have spent billions searching for life on the frozen, irradiated surface of Mars, yet we have never sent a dedicated mission to sample the atmosphere of our nearest neighbour. We have never floated an instrumented balloon in those clouds. We are finally changing that. New missions are being built to dive into that cloud layer and analyze its chemistry with unprecedented detail. Whatever they find, the answer will be historic. If they find life, even simple microbial life, it proves that biology is not a fluke. It suggests the universe is teeming with it, and if they find nothing, that too is a discovery. It forces us to define the absolute boundaries of habitability. The phosphine story was not a failure of science. It was science doing exactly what it is supposed to do. It gave us a surprising observation, forced a rigorous debate, and ultimately demanded that we build better tools to get a better look. We don't know if anything is alive in those acid clouds 50 kilometers above the surface, but we are finally going to go and find out. Chapter 8. The Return. There is a particular feeling that comes with returning to somewhere you've neglected, a mixture of guilt and excitement. For the better part of 4 decades, Venus, our nearest neighbour, our twisted twin, our solar system's most dramatic cautionary tale, has been largely ignored. The last time anything landed on its surface was 1982. Since then, we have mapped it from afar, but we haven't truly reached out to touch it. That is about to change. In a surprise shift, NASA has greenlit 2 major missions to Venus. The first is Da Vinci. It won't land, it will fall. It will descend slowly through the atmosphere on a parachute, spending an hour sampling the air chemistry in extraordinary detail. In its final minutes, it will photograph a region called Alpha Regio, some of the oldest exposed rock on the planet. One brief, falling look is more than we have had in 40 years. The second is Veritas. It will stay in orbit to create the highest resolution radar map of the Venusian surface ever attempted. It will track geological changes, identify active volcanoes, and definitively answer the question, is the planet alive right now? They aren't alone. The European Space Agency is developing Envision, a probe designed to look beneath the surface, studying the plumbing of Venus's volcanic systems. These missions are ambitious, but they are only the beginning. Teams are already designing long-term balloon missions, platforms that could float in that temperate 50-kilometer zone for weeks, sampling the clouds for signs of life. Why does this matter? For most of the space age, our narrative has been about Mars. Mars as the next frontier, Mars as the potential second home. That story is important, but it has crowded out the story of Venus. Venus is not a story about where we might go next. The surface of Venus is not a place for humans. It is not a backup plan. It is a story about where we already live. Venus is the most extreme example of planetary climate collapse in our solar system. It is a world that tipped from a potential paradise into an oven. Studying it isn't just about rocks and clouds, it's about reading the warning signs of how a planet can change. It is about understanding the thresholds we must never cross. The next generation of missions will have better instruments, faster computers, and more daring designs than the Soviet engineers of the 1960s could have ever dreamed. But they are built on the same core impulse. We want to know. We have always wanted to know. Venus, patient, bright and terrible, has been hanging in our evening sky for billions of years, waiting for us to stop looking away. It is waiting for us to come back and ask the right questions. We are finally ready. Chapter 9. The Ultimate Warning. We have come a long way tonight. We started with a steady, brilliant light in the evening sky. We travelled through lost oceans, runaway heat, and crushing atmospheres. We stood on a surface hot enough to melt lead, in a silence broken only by the slow, volcanic breathing of a world that refused to give up its secrets. We honoured the engineers who sent their machines into that furnace, and we looked toward the new missions that will soon return to ask the questions we should have been asking for decades. Now, I want to bring it home, because every detail we have discussed, every horror, every mystery points to one place: this planet, the thin, improbable, precisely calibrated envelope of gas and water that makes this room and everything in it possible. Venus and Earth are twins. They formed from the same material in the same neighborhood at the same time. For 2 billion years, Venus likely held liquid oceans. It was, by every indication, a world that could have hosted life. Then it lost everything. It didn't lose its life to an asteroid or a solar explosion. It lost it to chemistry, to a runaway feedback loop of carbon dioxide and water vapor that, once started, could not be stopped. Venus crossed a threshold, and on the other side of that threshold was a world that could no longer support the conditions it had spent billions of years maintaining. There was no warning, no moment where someone could have pointed and said, "There, that is the point of no return." Change was slow until it was fast. Then it was complete. The mechanism that destroyed Venus is not alien physics. It is the same process, the same gas, the same equations that we are currently running as a global experiment on our own planet. I am not saying Earth is about to become Venus tomorrow. We are further from the Sun. We have magnetic fields and geological cycles that act as buffers. But buffers are not immunity. The question Venus forces us to confront is not about tomorrow. It is about thresholds. It is about the difference between a system that is stressed but stable and a system pushed past the point where it can recover. Venus is not just a warning. It is a laboratory. It is a natural experiment that has been running for 4.5 billion years. It has shown us exactly what the end state of a climate system looks like when the regulatory mechanisms fail. It is a monument to what happens when a world is pushed past the point of recovery. It has been there for billions of years, and it will be there for billions more. It is extraordinarily patient. The question is whether we are paying attention. I think often of the Venera engineers. They were given an impossible task, and they responded by calculating the exact window of survival and designing right up to the edge of it. They failed, they learned, they tried again. That capacity to look at an insurmountable problem, to bring every tool and mind to bear on it, to fail and learn and try again, is the greatest expression of human curiosity. That is the capacity we need now, for a problem closer to home, with higher stakes. Venus is not a story of despair. It is a story of attention. The universe has handed us a vivid, unambiguous example of what happens when a climate system fails. It has given us a laboratory we didn't have to build, delivering results we can study from the comfort of our own home. That is, in a strange way, a gift. A gift wrapped in sulfuric acid and delivered at 465 degrees, but a gift nonetheless. We know the warning signs. We know the mechanism. We know the cost of getting it wrong. What we do with that knowledge is up to us. It has always been up to us. Look up on a clear night, just after sunset. Find that steady, brilliant light. It is too bright to be a star. It is beautiful in a way that still catches the breath, even knowing exactly what it is. That is Venus, our twin, our warning, our mirror. And if we are paying attention, if we take the lesson it has spent 4.5 billion years preparing for us, perhaps finally our teacher,